I welcome everyone to this session on weather radar and its use in forecasting. In this slide itself, in this first slide itself, what you see as this footboard-like structure, most of you must be familiar with it. If you are staying in Panji, you must have seen such a structure on Altino, which is called the radome. Inside it is the antenna of radar, which functions 24/7. The size of Doppler weather radar antenna installed at Meteorological Center Goa is uh, around 8.5 meters in dia, and this radome is around 11.5 meters in diameter. This is made of a special material, fiber reinforced plastic, which has a very less radio frequency absorption. So this is about the structure that you must be already familiar with, but not quite sure what it is. One by one, let's go into the slides of this presentation, and let me share you more details about the Doppler weather radar that is installed at IMD Goa, and also about the general features and general principles on which weather radar and Doppler weather radar works. So when we talk about weather radars, their history starts from around 1920s. There were experiments conducted by scientists in US to track a moving ship using electromagnetic radiation, electromagnetic waves. And then in World War II, these instruments were radars were extensively used to track down and shoot down moving objects such as aircrafts and ships. Then actually what the operators observed during the World War were when they were scanning atmosphere or scanning the skies using radars for enemy aircrafts, they found some noise which were actually not helping them to identify the actual targets, which were covering these noises or unwanted echoes were covering the actual targets. And then later it was realized that the noise or this echoes, unwanted echoes, are actually due to weather features, which were a hindrance at that time for radar's operation, which was to track enemy aircrafts. Later it was identified that this information can be used constructively. Radars can be made particularly to track or identify significant or severe weather, and it can help in disaster management activity. The first photograph of a hurricane using radar was taken on 14th September 1944, and in by around 1970s and 80s, radar became a good tool or a very useful tool for monitoring and identifying significant weather events. NOAA started using it in regular operational forecasting from around 1980s. They installed around 200 number of S-band Doppler weather radars, and this network was called NextRad network, and that was very I mean that was the backbone of significant or severe weather forecast that was being issued in US in the 1980s. The first Doppler weather radar in India became operational in 2002 at Chennai. Now this is the existing radar network in India. We can see that almost 30 number of Doppler weather radars are already in operation. Along with that, so many are being installed at different places of the country, such as the West Coast. There are proposed installations to carry on. There are more installations to carry out, and replacements are being carried out on the eastern coast of the country for radars, weather radars, Doppler weather radars. And you can notice here that the number of radars on the eastern coast are comparatively higher, because we know that Bay of Bengal is more prone to cyclones than the number of cyclones they form over Arabian Sea. And along with that, there are radars being installed in the Himalayan range for weather forecast of significant weather features there. And all these radars, they may not be of the same category, they may not be of the same size, same power, or same purpose, the kind of weather features they are intended to observe, they could be different from each other, and accordingly the shape, power, all those things could be the size, all those things could be different from radar to radar. Just taking an example, what all radars that are installed over the coastal lines are S-band radars, which are supposed to track and identify cyclones. They are the they these instrument S-band radars obviously require a bigger set of equipments. The antenna should be bigger in size. Whereas if you're talking about inland radar, such as the one in let's say Delhi, that need not be a S-band radar, because the range one has to see from Delhi need not be over the oceans. If we are talking about Goa, we want to see about 500 kilometers distance over oceans, because that's where the cyclones form. But in case of a place like Delhi, we need to monitor a comparatively lesser range of area. So the atmospheric properties are different there. The kind of weather that forms there is different. So for such cities and for urban meteorology, it's C band or X band radars, which are comparatively smaller in size, and which are used for comparatively lesser area of range. So the whole purpose of telling this is the radars could be different at different locations based on the requirement at that particular location. Now, if we go to the history of this storm tracking or storm identifying analog radars, the old generation of radars, they did not have any digital kind of display. They were basically CRT monitors, where the significant weather signatures will flash like a light or some reflection when the scanning of radar goes through that particular area. So most of the times these signatures formed had to be taken a photo of, or they had to be copied onto a tracing paper, keeping the paper on top of this CRT monitor. So that's how difficult it was in the older generations to uh, infer or even to save the information that was received from a analog weather detection radar. So this image we see here is actually a series of images. I'll take one by one. I'll take you to through them one by one. So the image was taken in 1950s, and these were not the kind of sophisticated or uh, highly powerful radars that we use now. This was probably a smaller radar. Uh, more more of it was used for study or to research purpose or to improve the technology rather than operational weather forecasting. So what we see here is that on the top, on the north side of this, let's consider this is the point where the radar was installed, and this is the white patch you see here, that's actually a cloud, echo coming from a cloud. So in alternate images we can see that the cloud is actually moving. There are some changes that is taking place in this cloud mass, and it is this point at this point you can see a hook-like structure here. This hook-like structure is a uh, echo from a tornadic thunderstorm. So that's what the conclusion was. This is how a thunderstorm or a tornadic thunderstorm, which is such a strong phenomena that was seen in analog radar in the 1950s. So that's exactly what the description says here. In 1953, Donald Stagg, an electrical engineer working in the Illinois State Water Survey, made the first recorded radar observation of a hook echo associated with a tornadic thunderstorm. Now we have seen the analog radar, how it functions, how it captures a weather event. Now let's see how modern era radar, Doppler weather radar, see significant monsoon clouds, and let's see the animation of that. So this is from 22nd 21st of July and 21st to 23rd early morning. That was the day when there was a flood-like situation over Goa, and we observed that by around 10 p.m. of 22nd of July there were strong clouds, strong echoes which can give torrential rainfall. High intense spells were noticed. So accordingly, we issued a impact-based forecast, and we forecasted that there could be possibility of flooding and flash floods over that particular region, eastern parts of the state, and that is exactly what happened. And why this image is so important is that it tells us how far the technology has come forward, how the outcomes have changed, how the presentation of data has changed from an analog radar. Uh, so the purpose of showing this particular animation was to have feel the difference between the older era radars and the present generation of radars. Now, similar is the case with a thunderstorm. This was in 2018 October, and here we can see the signatures. We can identify the systems from one another. We can see the um, genesis, its intensification, its movement. Everything is very clear. The sharp edges are there. The differentiation can be easily made from a clouded area and a cloudless area, and all this was quite difficult in the radars, analog radars. What exactly is a radar? Radar is an acronym for radio detection and ranging. That means it is using radio waves, waves of the frequency uh, of the order of gigahertz, and it is with that radio wave or radio frequency signal, or electromagnetic signal, it is trying to detect and identify the location of significant weather events. Now, how does a radar work? We will discuss in detail about the basic principle of radars working, and to uh, to understand that, let's visualize a music concert. Let's see how uh, music concert can be compared, or how it is analogous to a uh, radar's operation. Let's see that. So let's consider a singer or a band here for the purpose of understanding. Instead of electromagnetic waves, I'm going to explain this principle on the basis of audio waves or sound waves. So let's call this person a soda. He is using sound waves for detection and ranging. So let's call this band for our understanding as soda. Now here uh, in front of this person there is a huge crowd. There are so many number of people there. They are listening to his music, but what stands out is a set of his die-hard fans who are actually singing back to him whenever he is asking them to. So the purpose of Mr. Sodar is to identify how many of such his die-hard fans are there in this crowd and where they are situated. So that's what the ultimate purpose of this singer is, to know. And let's see where these people are exactly, and how this person is trying to identify their location and their distance from him. uh, we can see there are four clusters actually, 1 2 3 and 4. These are the actual clusters or the set of people who are at a frequency sync with him. Let's say they are in frequency sync with the singer. uh, Whenever the singer asks them to sing back, these people are going to sing back to him, and they qualify as his die-hard fans for our understanding. So when he sings, they sing back to him, and then again when he sings, they all sing back to him simultaneously. But what you must have noticed now is that when they are singing, it's the cluster which is the closest to him, is the closest cluster sound that reaches him first, and then the second closest, and then the third, and finally the farthest one. So the farther they are from the singer, the slower or the more time it takes for their sound to reach to the singer. Now let's see how this singer is making use of this information. The singer is not a layman. He has some knowledge about physics. He's a physics graduate, let's say. He thinks like a physicist, and he knows the following. He knows at what speed a person's sound travels in atmosphere. He knows what's the intensity of one person's sound, and then he also knows that at what rate the sound of one person fades with respect to each 5 meter distance. That means the sound will not be the same intensity when it reaches the singer. It will definitely fade, or its intensity will decrease. So he knows at what rate the sound intensity is decreasing. Then he knows the speed of the sound, and he knows what is the intensity of sound that a single one of his uh, die-hard fan makes. So what he does here is he's intelligent. He knows how to make use of the information for his benefit. So if he tells everybody to sing back to him, then what he will be getting is noise pollution rather than any significant information. So what he does here is he points his hands to one side of the crowd, and he tells them to sing back. So once he points his hands to one direction, let's say if we compare here, uh, this upward direction as north, then he points his fingers to the northeast direction of the crowd, and he sings to them. So the crowd sings back. Now let's see what happens. This is important to note. He points to one direction, and after singing he listens for response. That means he's cautiously, curiously waiting for the response noise to come to him. He's not keep on talking or keep on singing. He will speak one note, and then he will wait to understand how long it takes for the sound from the uh, cluster of that fan to come to him. From that he estimates the time. He counts the time, and from that time he estimates how far the people are, because he already know what's the speed of sound on atmosphere. So he can easily calculate at what distance these people are, if he knows how much is the time taken for their sound to travel up to him. Now third, he knows at what rate is the sound is supposed to fade per 5 meter, or let's say 5 or 10 meter or anything. So once he knows the distance, he can estimate. If he knows the intensity of the sound that reached him, and he knows what is the distance of these people from him, he can estimate, or he can extrapolate what could have been the actual intensity of the sound when they all made it at the place where these people are sitting or standing. So now that he has two information, he has the distance from where these people uh, sang back to him, and he knows the intensity at which these people sang back to him. Now the other thing is, he knows the intensity of single man's noise or single woman's noise, and from that he can easily calculate now how many people are there in that particular cluster at that particular direction. Now he repeats the same thing, pointing to the other direction. People sing back to him, and obviously this time that uh, uh, sound is going to take a little bit more time, because that is the farthest uh, distance where the cluster is situated. Now from that also he estimates the distance. He listens for response, he calculates the distance, and from the rate of fading sound he estimates what could have been the actual quantum of sound that was made by this cluster of fans at that distance. And from that, since he know the single person's noise level or sound level, he can estimate how many people were there in that particular direction. Now the same process is repeating for the third cluster and for the fourth cluster as well. So now ultimately at the end of this exercise, what he has in his hand is the exact information, like in which direction his diehard fans are sitting, and at what distance they are sitting from the podium, and how many of those people are sitting there in each of those clusters. So that ultimate information he gets by this uh, easy exercise and a lot of calculation and the knowledge of a few uh, physical realities. Now this is exactly what a radar also does. What a radar does is, it also points to different directions in atmosphere, and whenever it is pointing to one particular direction, it will transmit electromagnetic waves in that direction. It will then listen for a certain duration to get the response back from the potential hydrometeors, and then it will do the scanning at that particular elevation angle. Elevation angle is the angle we say that the antenna's feed horn makes with the ground. So at one certain angle, at one certain elevation angle, it will scan the entire atmosphere. Then if that is over, then it will change its elevation angle, and then once again it will do the 360-degree scanning, and this process continues. Whenever it is rotating, it is transmitting as well as listening, and the order of this transmission and listening times is in the order of microseconds and milliseconds. So even though we may feel that the radar is quickly scanning, for every millisecond of its rotation, it's transmitting as well as receiving. We will see in details about these pulses and the listening period. All that we will see in detail in the coming slides. Now the assumptions here, we were comparing the singer to a radar or a sodar or a sonar in technically actually, and there are some assumptions that has to be there, otherwise the entire calculation will go wrong. The first thing is everyone in a diehard fan cluster is singing back at the same voice level. It should not be that some people are singing at a lower voice, or that will lead to underestimation, and some people are singing at a higher voice, so that will lead to overestimation of the number of fans. Then second thing is only those fans in the pointed direction are singing. This is very essential. If all of them from different sides are starting to sing, then like we discussed, the person or the singer will get only a noise pollution. He will not be able to recognize anything properly. Now the fans sing exactly when he asks them to, not in advance or not late. This also is an important point. If somebody starts singing very well before what he tells them to, then the uh, singer may tend to estimate the people to be sitting very close to him, and this will also lead to error in the estimation. Now, those who are singing back are actually his diehard fans. They have to be, otherwise, if there are some people in the cluster who are not really his diehard fans but only want to add pollution, noise pollution to it, then also the person may end up calculating or estimating his fans in huge number than they are actually in real. And his ears are sharp enough to distinguish and evaluate intensity levels from one cluster to other. This is obvious. Unless his ears are, or the instrument he is using to recognize the intensity levels are sharp enough, he cannot estimate anything. So now these assumptions that we call, these are valid even in case of electromagnetic radiation and a radar. The errors that we have mentioned here, these can be there in the operation of a weather radar as well, electromagnetic wave radiation as well. When we are using electromagnetic waves also, all these kind of errors could creep in, and they all have different scientific or technical terms in case of electromagnetic wave radiation, or in case of Doppler weather radar. We will discuss about those possible errors also in the coming slides. So how Doppler weather radar works, we discussed about that. There are pulses of different width, actually two in number. They are two for two different purposes. One is of 1 microsecond and the other one is of 2 microseconds. And uh, after sending the radar pulse, the radar listens for the return signal, and this listening, or the listening period, or the waiting period, is of the order of milliseconds. Please note, the transmission takes place for microsecond, and the listening takes place for millisecond. That means the waiting period is approximately 1,000 times higher than the transmission period. Just scaling it up to the time that we humans can perceive. Let's imagine that a radar is transmitting a signal for 1 hour duration. That means it is going to wait for 100 hours to get some response back. 100 hours is approximately 40 days. So that's the kind of difference in time. Now we cannot perceive the milliseconds or nanoseconds or microseconds, but the radar is operating in those ranges using digital electronics, power electronics, or high frequency operations. So that's the time difference, or the scalable, if we are scaling it into our level, that's the difference between transmission time and listening time. Now, once it does this scanning process, at each elevation it will do a 360-degree azimuth scan, and that it will continue for all the pre-decided number of elevation angles, and finally what we get is a similar figure. This is the volume of atmosphere, the highlighted colors, the reddish orange or green colors. This is the volume of the atmosphere that radar is ultimately ending up scanning. And you can see that there is some cone kind of feature here. That means the area is right above the radar, where it cannot sense any signals until and unless one of the elevation angle is 90-degree, which is quite rare for operational Doppler weather radars to have. We have different equipments, wind profilers, which are for the sole purpose of scanning the area right above the instrument, but radars are actually intended to scan atmosphere of range 250 kilometers or 500 kilometers away from radar, and that's the purpose of it. And this is how structure of atmosphere or a volume of atmosphere will be once the scanning is done. And I'll just remind you, this area from this radar to one end is approximately 250 kilometers or 500 kilometers, or whatever be the range that has been predefined for that particular radar. Now, what is that information it is getting back? In case of Singer and his fans, it was voice, but here what it is getting back is backscattered radiomagnetic, I mean electromagnetic energy. Now there is some difference between reflection and backscattering. You can see whenever the wave goes and hits on a hydrometeor, it is getting splitted into numerous components, and it is getting dissipated into all the directions of the atmosphere, and a part of that energy only comes back if you can comprehend that the size of the wave that is going to that hydrometeor is quite big, but whereas the coming one is very small. But only thing to note is that both of them are of the same frequency. That's why we tend to say that the frequency matching of the singer and fan has to be there. Similarly, there has to be some certain frequencies which the radar has to transmit for a certain type of hydrometeor. It's not necessary that all the hydrometeors will respond for a certain wave of certain wave frequency of wave. There are pre-identified frequency ranges for which certain types of hydrometeors respond, and most of it is based on the um, dielectric property of the hydrometeor, then the size of the hydrometeor, and what frequencies it is those hydrometeors will absorb and backscatter.